They sold it as progress. Cleaner air, smarter engines, technology finally doing something good for once. On paper, it looked responsible. In real life, it looked like a tractor stuck in limp mode in the middle of harvest because a warning light decided today was the day. Before DEF, diesel engines were built with a simple philosophy: survive real work. They were overbuilt, mechanically tolerant, and forgiving. Bad fuel, cold mornings, heat, dust, vibration. None of that scared an old diesel. It might complain, but it kept running. Those engines did not ask permission. They did not negotiate with software. They did not shut down because a sensor disagreed. They worked until something physically wore out. That changed when emissions laws stopped respecting physics. Modern emissions regulations did not evolve slowly alongside engine technology. They arrived fast, aggressive, and politically motivated. NOx limits were lowered to levels combustion alone could not realistically meet in real-world conditions, especially in agricultural equipment that runs long hours under constant load. Engineers warned about it, manufacturers knew it, physics did not care, but regulations moved forward anyway. Manufacturers were given a choice: either redesign diesel engines from the ground up at enormous cost, or bolt on after-treatment systems that could clean up emissions after combustion was already finished. The second option was faster, cheaper, and easier to certify. That option is DEF. Diesel exhaust fluid was not created to improve engine durability. It was created to make emissions numbers acceptable on regulatory paperwork. Instead of solving the emissions problem inside the engine, DEF sprays a urea-based fluid into the exhaust stream to chemically neutralize nitrogen oxides after they already exist. On a test bench, it works. In a lab, it looks impressive. On a spreadsheet, it checks the box. Out in the field, it introduces an entirely new failure hierarchy. For the first time in diesel history, a chemical system was given authority over the engine itself. That is the real shift. A modern diesel engine can have perfect compression, stable oil pressure, clean injectors, and zero mechanical damage, and still be forced into derate or shutdown because the emission system is unhappy. Not broken, not worn out, not damaged, just non-compliant. This is a fundamental change in what engine longevity even means. Longevity used to be about metal fatigue, bearing wear, and hours of operation. Now it is about sensors, heaters, wiring, software logic, and chemical storage conditions. Components that do not age gracefully, and do not tolerate real-world abuse. DEF systems are fragile by nature. They rely on precise dosing, exact temperatures, clean fluid, functional heaters, accurate sensors, and constant electronic agreement between multiple control modules. When everything works perfectly, the system stays quiet. When one thing fails, everything stops. There is no middle ground. Older engines gave warning signs. Smoke change, sounds change, performance faded slowly. Operators had time to react. Modern emission systems fail digitally. Instantly. Binary. On or off. This is not reliability. It is enforcement. DEF freezes at roughly 12 degrees Fahrenheit. That alone should have been a red flag for agricultural equipment. To compensate, manufacturers added heaters to tanks, lines, and injectors. Heaters fail. Wiring corrodes. Thermal cycling stresses connectors year after year. DEF also crystallizes. That is not poor maintenance. That is chemistry. When DEF dries, it leaves solid deposits. Those deposits clog injectors, foul sensors, and restrict flow. Once crystallization starts, the system degrades rapidly. NOx sensors live in extreme exhaust heat and vibration, reading chemical reactions in real time. They are expensive, delicate, and notorious for false readings. When a sensor lies, the engine computer does not question it. It obeys it. The result is an engine that is mechanically healthy but electronically crippled. And when that happens, the solution is never simple. You cannot bypass the system legally. You cannot repair it without proprietary tools. You cannot ignore it and keep working. The machine forces you into compliance or inactivity. This is why older operators immediately recognized the problem. They did not need studies or explanations. They saw machines with fewer hours failing sooner. They saw repair bills rising without corresponding improvements in productivity. They saw engines that could have lasted decades sidelined by emissions hardware. DEF did not make engines cleaner in a meaningful, holistic sense. It made them conditional. Conditional on fluid quality, conditional on temperature, conditional on sensors, conditional on software updates, conditional on regulatory approval. That is not durability, that is dependency. And once dependency is built into the machine, longevity stops being the priority. Compliance becomes the goal. In the next part, we will break down why DEF system failures are not exceptions or mistakes, but inevitable outcomes of how these systems are designed, and why no amount of careful maintenance can change that reality. DEF system failures are not rare events. They are not caused by careless operators. They are not the result of poor maintenance habits. They are the natural outcome of stacking fragile systems on top of machines that are expected to work in brutal conditions. This is where the official narrative collapses. Regulators and manufacturers love to say that DEF systems are reliable when properly maintained. That phrase sounds reasonable until you examine what properly maintained actually means in the real world of agriculture. It means keeping a chemical fluid at the correct temperature year-round. It means ensuring that fluid never degrades, contaminates, or crystallizes. It means heaters always working, sensors always accurate, wiring always intact. It means software logic never disagreeing with physical reality. That is not maintenance. That is fantasy. Let's start with temperature, because temperature alone makes DEF unsuitable for agricultural equipment. DEF freezes at about 12 degrees Fahrenheit. In many farming regions, that temperature is not an exception. It is normal. Every freeze-thaw cycle stresses the system. Tanks expand, lines contract, heaters cycle on and off. Electrical connectors are exposed to moisture and corrosion. Heaters are consumable components, whether manufacturers admit it or not. They burn out, they fail partially, they draw uneven current, and when a heater fails, the system does not politely notify the operator. It escalates. Cold DEF means inaccurate dosing. Inaccurate dosing means emissions non-compliance. Non-compliance means derate. Now add crystallization. DEF is a urea-based solution. When exposed to air or heat, it leaves behind solid crystals. This is basic chemistry, not operator error. Those crystals form inside injectors, on sensors, and in dosing lines. Once crystallization begins, it accelerates system failure. A partially clogged DEF injector does not simply reduce performance. It creates false sensor readings. The engine control unit interprets this as an emissions violation, not a mechanical issue. Again, the engine itself is fine. The punishment is still severe. Then there are the sensors. NOx sensors operate in one of the harshest environments on the machine. Extreme heat, constant vibration, chemical exposure. These sensors are expected to provide precise readings for years under conditions that destroy far simpler components. They fail, often. Sometimes they fail completely. Sometimes they drift slowly out of calibration. Sometimes they produce intermittent errors that are nearly impossible to diagnose. The control system does not know the difference between a bad sensor and a dirty exhaust stream. It trusts the sensor, and the system reacts aggressively, because regulations demand it. This is where modern diesel engines diverge completely from older design philosophy. Older engines assumed components would fail and allowed for degradation. Modern emission systems assume perfection and punish deviation. There is no tolerance built into the logic. A single faulty reading can trigger a countdown to derate. A second reading can trigger speed limitation. Ignore it long enough, and the machine immobilizes itself. Not because it cannot run, but because it is not allowed to. This creates a reliability paradox. The more complex the emission system becomes, the more points of failure it introduces. Each additional sensor, heater, pump, and control module reduces overall system reliability. This is not opinion. It is systems engineering. Complex systems fail more often than simple ones. Manufacturers know this. That is why redundancy exists in aviation and medical equipment. But agricultural machinery does not get redundancy. It gets enforcement. One failed component disables the entire machine. And when that happens, the operator has very few options. Independent repair is often impossible due to encrypted diagnostics and proprietary software. Temporary fixes are blocked by design. Bypasses are illegal or electronically prevented. Even identifying the true cause of failure can require dealer intervention. This is not accidental. Emissions compliance shifted control away from the owner and toward the manufacturer and regulator. The machine no longer belongs fully to the person who paid for it. It operates under conditions imposed by external authority. This is why DEF-related downtime feels different than traditional mechanical failure. It is not frustrating because something broke. It is frustrating because something arbitrary took control. The engine didn't quit, the law did, and here is the most important point. Even if every DEF component were replaced perfectly, the system would still fail again. Not because of neglect, not because of abuse, But because the operating environment of agricultural equipment is fundamentally incompatible with the fragility of emissions after treatment systems. Dust does not respect sensors. Cold does not respect heaters. Vibration does not respect wiring diagrams. You cannot engineer regulation-proof hardware into a machine that lives outdoors, works under load for thousands of hours, and is expected to last decades. DEF systems were designed to pass certification, not to age gracefully. That distinction explains everything that follows. In the next part, we will confront the biggest myth of all, that these systems meaningfully reduce environmental impact when real-world operation, fuel use, downtime, and shortened machine lifespan are taken into account. Because when longevity is sacrificed, the math changes. This is where the conversation usually gets uncomfortable. Because once DEF systems start failing, the defense is always the same. Yes, it's inconvenient, but it's cleaner. That sentence ends debate without ever proving its own claim. Cleaner compared to what? Cleaner under which conditions? Cleaner over how many years? In laboratory tests, DEF systems reduce NOx emissions. That part is true. The problem is that laboratory tests do not represent how agricultural equipment actually operates, ages, or gets used in the real world. A tractor on a dyno is not a tractor in a field. In real operation, DEF systems introduce inefficiencies that quietly erase much of the theoretical environmental gain. Regeneration cycles increase fuel consumption. Derate modes force engines to operate longer at inefficient loads. Idle time increases while operators wait for systems to clear faults or complete regen cycles. Fuel burned per acre goes up. That alone should raise questions, but it usually doesn't, because the emissions discussion is narrowly framed around tailpipe chemistry, not total system impact. Then there is downtime. When a machine derates or shuts down due to an emissions fault, the work does not disappear. It gets delayed, rescheduled, or transferred to another machine. That often means running older equipment longer, hauling replacement machines farther, or operating at suboptimal times. All of that increases fuel use. But the biggest blind spot is lifespan. Historically, diesel engines in agricultural equipment were long-term assets. 30 years of service was not unusual. Even when the chassis wore out, engines were rebuilt and reused. Longevity was built into the environmental equation whether anyone acknowledged it or not. A machine that lasts longer has a smaller manufacturing footprint per hour of work performed. Modern emissions systems disrupt that equation completely. DEF systems and their supporting electronics often become economically unviable to repair long before the engine itself is worn out. When repair costs exceed perceived value, machines are scrapped early, parked permanently, or sold into secondary markets where emissions compliance is ignored out of necessity. Scrapping a machine early is not environmentally neutral. Steel, aluminum, copper, rare earth elements, plastics, and electronics all carry massive embedded energy costs. Manufacturing a replacement machine produces emissions far greater than what DEF systems save in their early years of operation. This is not speculation, it is basic lifecycle analysis. If a tractor lasts 10 years instead of 30, you have effectively tripled its manufacturing footprint per hour of work. No amount of tailpipe chemistry can offset that loss. Yet emissions policy almost never includes lifecycle durability in its calculations. Why? Because durability is hard to regulate, hard to measure, and impossible to enforce through software. It is much easier to regulate chemical output at a single point in time than to design policy around long-term mechanical resilience. So the system optimizes what it can measure, not what actually matters. This leads to absurd outcomes. An older pre-emissions tractor running efficiently for decades is labeled dirty, while a modern machine that fails prematurely due to emissions hardware is labeled clean, even if the total environmental cost is higher. This is accounting, not environmental stewardship. There is also a behavioral effect nobody likes to discuss. When operators know that emission systems are fragile, they change how they use equipment. They idle more to avoid regen interruptions. They avoid shutting machines down in cold weather. They plan work around warning lights instead of field conditions. These behaviors are rational responses to system design, but they increase fuel use and reduce efficiency. Again, the math moves in the wrong direction. DEF also shifts emissions geographically rather than eliminating them. Urea production, DEF transportation, plastic containers, and disposal all carry their own environmental costs. These are simply moved upstream, out of sight, and out of regulatory focus. The emissions did not disappear. They were outsourced. And then there is the issue of forced obsolescence. When emissions systems are integrated so deeply that they cannot be economically repaired outside dealer networks, machines become disposable by policy, not by necessity. That accelerates replacement cycles, increases capital consumption, and raises the environmental cost of agriculture as a whole. This is why many experienced operators instinctively reject the clean diesel narrative. Not because they oppose cleaner air, but because they understand trade-offs. They know that durability is environmental responsibility. They know that efficiency over decades matters more than compliance on paper. They know that a system that fails early is not green, no matter how good it looks on a report. In the next part, we will stop pretending this outcome was accidental. We will examine who benefits financially from DEF systems, why independent repair was quietly sacrificed, and how emissions compliance became a permanent revenue stream instead of a technical requirement. Because bad systems survive when they are profitable. At some point, it becomes impossible to believe this system survived by accident. Because when you step back and look at who benefits from DEF and modern emissions architecture, the incentives line up too perfectly to ignore. Start with the manufacturer. In the past, selling a tractor was largely a one-time transaction. Yes, there were parts, filters, and maintenance, but the core value of the machine belonged to the owner. If something broke, it could be fixed. If it wore out, it could be rebuilt. Control stayed in the field. Emission systems changed that balance. DEF hardware, sensors, and control modules are not just components. They are gatekeepers. They decide whether the engine is allowed to operate. And crucially, they are tightly integrated with proprietary software that only manufacturers and authorized dealers can access. This turns repair into a controlled service, not a mechanical task. A failed NOx sensor is no longer a simple diagnostic problem. It becomes a software event. A locked fault code, a system that refuses to clear until the correct sequence is followed with the correct tool, often connected to a remote server. That means downtime. Downtime means dependency, and dependency is profitable. Dealer networks benefit enormously from emissions-driven complexity. Jobs that used to take hours now take days. Diagnostics that used to be mechanical are now electronic. Parts that used to be interchangeable are now serialized and coded. Every failure funnels the owner back to the dealer. Independent repair shops are locked out by design. Farmers who once fixed their own equipment are told they're tampering if they try to regain control of a machine they already paid for. This is not safety. This is not environmental protection. This is market control. DEF systems also create recurring consumption. DEF fluid itself is not free. Storage matters. Quality matters. Contamination matters. The machine depends on a consumable chemical to remain operational. No DEF, no work. That alone should have raised alarms, but it didn't, because the cost is spread slowly and normalized as the price of modern equipment. Manufacturers also benefit from shortened machine lifespans. When emission systems become too expensive to repair relative to machine value, replacement becomes the default option. This accelerates sales cycles. Machines that could have worked for decades are replaced in half the time. This is called planned obsolescence when it happens in consumer electronics. In agriculture, it is politely called regulatory compliance. Regulators benefit as well, though not financially in the traditional sense. They benefit by being able to claim progress. They benefit from easily measurable metrics. Tailpipe numbers, compliance reports, inspection data. These are simple to track and easy to defend politically. Long-term durability is harder. Lifecycle analysis is messy. It introduces uncomfortable questions about whether policy actually reduced harm or simply shifted it. So durability is ignored. The farmer absorbs the cost. Higher purchase prices, higher repair costs, higher downtime risk, lower resale value, and less control. This is why right to repair became a serious issue only after emission systems took over. The fight is not about convenience. It is about ownership. If a machine can be remotely disabled, electronically restricted, or software locked due to a chemical system failure, ownership becomes conditional. The operator is no longer the final authority. The machine works as long as it agrees with the system that governs it. This changes behavior. Farmers begin to see equipment not as long-term investments, but as depreciating liabilities. That mindset affects purchasing decisions, maintenance strategies, and even farming practices. Trust erodes, and once trust is gone, people start looking for ways around the system. That is why pre-emissions equipment prices continue to rise. That is why gray market imports exist. That is why bypass kits appear, despite legal risks. These are not acts of rebellion. They are survival strategies. When a system becomes hostile to its users, they will work around it. The uncomfortable truth is that emissions compliance created an ecosystem where failure is profitable and durability is optional. As long as machines meet regulatory targets during certification, their long-term reliability is someone else's problem. And that someone else is the farmer. In the final part, we will look forward, where this path leads, what it means for the future of diesel engines in agriculture, and why the tension between regulation and reliability is reaching a breaking point. Because systems that ignore reality eventually collide with it. Every system reveals its true priorities over time, not in press releases, not in regulatory language, but in how it behaves after 10, 15, 20 years of real use. Modern emissions-controlled diesel engines are revealing theirs now. They are not designed to age. They are designed to comply. That distinction explains everything that feels wrong to experienced operators. The shortening lifespan, the rising downtime, the sense that machines are becoming less trustworthy despite being more expensive and more technologically advanced. This is not technological regression. It is a shift in design incentives. When emissions compliance becomes the primary requirement, longevity becomes secondary. Engineers are no longer rewarded for building engines that last decades. They are rewarded for passing certification, minimizing warranty exposure, and integrating systems that enforce regulatory behavior. Once that mindset takes hold, durability stops being a goal and becomes a liability. A machine that lasts too long delays replacement sales. A machine that can be repaired independently reduces service revenue. A machine that tolerates abuse undermines control. So tolerance is engineered out. This is why modern engines feel fragile even when they are mechanically sound. The weakness is not in the metal. It is in the logic governing it. As this continues, several predictable outcomes emerge. First, equipment turnover accelerates. Machines are replaced not because they are worn out, but because emission systems become economically unjustifiable to repair. Owners are forced into new purchases earlier than planned. Capital costs rise. Debt cycles tighten. Second, operational risk increases. When machines can derate or shut down unpredictably due to non-critical failures, operators lose confidence. Work planning becomes defensive. Backup equipment becomes necessary. Efficiency suffers. Third, the market splits. On one side, highly regulated, software-controlled equipment with high costs and limited ownership rights. On the other, older pre-emissions machines, gray market imports, and increasingly, illegal modifications. This is not because farmers want to break rules. It is because the system leaves them no practical alternative. When compliance threatens livelihood, compliance loses moral authority. Regulators often respond by tightening enforcement, increasing penalties, and expanding monitoring. That escalates the conflict but does not resolve it. It treats symptoms, not causes. The root problem is this. Emissions policy was written without respect for how agricultural machines live, age, and fail. A tractor is not a commuter car. A combine is not a delivery van. Farm equipment works long hours, under load, in environments hostile to fragile electronics and chemical systems. Ignoring that reality does not make it go away. It just shifts the cost downstream. There is also a cultural consequence. Generations of farmers were raised with the idea that owning equipment meant understanding it, fixing it, maintaining it, passing it down. Emissions architecture breaks that relationship. Machines become sealed objects, black boxes, dependent on external permission to function. That erodes not just trust, but skill. And once skills are lost, dependence deepens. This is why right to repair is not a political slogan in agriculture. It is a survival issue. It is about preserving the ability to work without being digitally supervised by systems that do not understand context. DEF did not create this future alone, but it symbolizes it perfectly. A chemical fluid that determines whether an engine may run, not because it affects mechanical health, not because it protects the machine, but because it satisfies a regulatory condition. That is not engineering serving agriculture. That is agriculture serving policy. None of this means emissions do not matter. Clean air matters. Responsible engineering matters. Environmental stewardship matters deeply to people who live and work on the land. What does not work is pretending that durability is optional. The cleanest machine is the one that lasts. The most responsible engine is the one that does not need to be replaced prematurely. Any policy that ignores that truth will continue to fail in practice, no matter how good it looks on paper. The DEF system is not a scam because it reduces emissions. It is a scam because it was sold as progress while quietly destroying longevity. And longevity was never the problem that needed fixing.